All right, astronomy, Wednesday. I think it's maybe the 8th. I don't really know anymore. I kind of lost track of dates here, but I want to give you a little heads up on where we're going. We're looking at Unit 7 now, the death of stars, what they turn into. There was an assignment put out with Level 1 being putting in order what happens to a low-mass star throughout its lifespan as it develops and dies. Level 2, as you go through a little digital textbook and answer some questions about the life cycle and death cycle of stars. I'm kind of walking you through some notes here, a little extra above and beyond with the high mass stars, all the cool stuff it turns into. So we'll do that for you in a sec. And then you have the little short story on Voyage Among the Holes. The grades for Unit 6 were put in. Shout out to Suter for reminding me that I hadn't opened those up and turned them to the student scores. So those are now available, so you can look at the student scores link and check what you did. I still do have to go back to Unit 5 and update those things, but then by this weekend we should have a good picture of what you've gotten for 5, 6, and 7 as we move forward. Okay. So as we continue on here, let's take a look at the notes that I've got here on the screen. And in order to understand what comes beyond, yesterday we did neutron stars and pulsars, right? So you're talking about a star that's 10 times the mass of the sun, squished down to the size of a city. And that is going to create really high gravities. Now, to show you what that is, we have to understand gravity, and I'm going to flip you over, and I'm going to have you come down here and just take a look here at the gravity equation again, right? The gravity equation is the force of gravity equals some constant, meaningless, right? Gravitational constant. The mass of the objects, right, multiplied by each other, and the distance between them, we'll call it d squared, okay? So if I'm talking about something that is 10 to 100 times the mass of our sun, big masses, that top part of the fraction becomes huge, right? And I'm talking about squishing those into teeny tiny little spots. That means that this distance, or the size of the star, the distance from the top to the middle, is going to get smaller and smaller and smaller. Well, what happens when you take something, let's say 10 divided by 2, that equals 5. Right? Now let's ratchet this up and let's ratchet this down. Let's make this 100 divided by 1. 100 divided by 1 is no longer 5, right? That is 100. So that's a big difference when you're talking about lowering this denominator and increasing the numerator. Okay? So when you take bigger masses of stars and you squish them into ever smaller places, the gravity skyrockets, the amount of gravity, right? So if we understand what gravity is, okay, which is, as Einstein figured out back in 1905, that it's those warps in space-time. The more gravity you have, the stronger that pull down on the fabric of space-time, right? And so for the Earth, you throw a ball 25,000 miles per hour, and it leaves and never comes back. Okay? The more gravity you have, the faster that escape velocity would have to be. Until you get to something that is such a high escape velocity, let me just find what I'm talking about, like a black hole, right? So here's an object that has such a high escape velocity that I throw a ball, a photon of light, at the speed of light, and it just arcs back down, as you can see in this picture here, like a ball tossed not fast enough to leave the Earth, right? It arcs back down. So this becomes a pretty weird object. It's still something there, but its gravity is so strong that you can't see it, because any light trying to reflect off of it and come off, or just leave it internally, just falls back down to it and can't leave the surface. Okay? So we're going to get into some more of the implications, because you've got more than just, oh, this thing called a black hole I can't see. Right? There's a lot going on here, because Einstein also said that space and time are not separate things. This little web here, right? This fabric of space-time, as it's called, Einstein says that the lines running one way are space, the lines running the other way are time. These are interwoven with each other. Okay? So if I stretch space, I am stretching time as well, right? And we're going to kind of get into the implications of what this means. Typically at this point of the semester, we'd be watching the movie Interstellar, where they go and they orbit a black hole and all kinds of time warp issues take place. An hour ends up being 15 years or something. And they do a really good job because they had a actual black hole scientist as their science advisor. In fact, the short story you're reading, and I'll bring my camera up so I can actually talk to you. The short story you're reading right now, Voyage Among the Holes, is the intro to a book about black holes written by this famous scientist Kip Thorne, who that story, Voyage Among the Holes, actually became the motivation for the movie Interstellar, right? So oftentimes these short stories get adapted and thrown here and there. We'll actually take a look at another short story later that turned into a major movie called Arrival about aliens and time. I wanted to give you a taste of Interstellar. I can't say, oh, go out and watch Interstellar now. If you have access to that, great, go watch Interstellar. It's a great movie and it's really well done. But I can't say, everybody get yourself a subscription to Prime or whatever and watch Interstellar, and I can't necessarily copy it and put it on Schoology. That wouldn't be right, would it? Oh, maybe. Well, we'll see. Maybe I'll be able to act out Interstellar at some point, and we'll just put on the whole production right here in my studio. We'll see. Anyway, I wanted to give you a little taste of black holes. We'll come back Thursday and do that, but keep doing what you're doing with Unit 7. If you have any questions, of course, let me know. Otherwise, we'll send you off there.